Thank you everyone for being here today. I'm very excited to introduce my research on human-centered spatial-temporal modeling and simulation in the era of infrastructure. So we live in a dynamic 3D world. We are seeing massive spatial-temporal data being generated and used in every aspect of our daily life, such as social media, entertainment industry, transportation, and many other activities. Over the past decade, we have seen the significant impact of AI and machine learning in transforming infrastructure research. For example, if you check the McKinsey report on the impact of AI on different industry sectors, you will see that AI can potentially create about 40% of the overall 9.5 trillion to 15.4 trillion annual values by all data analysis techniques. It is obvious that building infrastructure will have a significant impact on society, affecting people's lives in various ways. Taking the transportation infrastructure as one key example, as stated by the US DOT, to deliver the world's leading transportation system could serve the American people and goods through the safe, efficient, sustainable, and equitable movement of people and goods. So what does it mean to us? It means safety and zero fatalities to all. According to the National Highway Traffic Safety Administration, more than 42,000 people died in motor vehicle crashes in 2021, the most since 2005, and an average of more than 110 deaths every day. Therefore, building a safe transportation system will significantly reduce fatality and deaths. Also, it means equitable mobility for all. Imagine a world where no matter where you live, how much money you have, or who you are, you will have access to safe, frequent, affordable, seamless transportation options that serve your need. In this world, transportation is no longer a barrier to accessing job or education opportunity, medical appointments, recreation, or childcare. It is also important to note that the roadway fatalities are not evenly distributed across the United States, which is influenced by a range of factors, such as where the national population centers are located, which is highlighted in the left map, depicting the overall roadway fatality per state. The right map illustrates the divergent fatality rates among the states, which highlights the heterogeneous nature of the national safety problem. One major factor that explains the difference in fatality rates is whether a particular state is predominant rural or urban. And nationwide, the rural fatality rates is approximately 2 times higher compared to urban fatality rates. So I hope this will highlight some of the importance of building advanced transportation infrastructure. Beyond the transportation, we have seen many other infrastructure systems for healthcare, climate change, smart building, and so many more. More importantly, many of them are powered by AI and machine learning techniques. I'd like to share a big picture of my current research. It's basically consisting of 4 components. the spatial temporal data infrastructure where you digest or collect data from multi sources or multi sensors. You also have the ecosystem to integrate both physics and simulation component of an underlying transportation system. And on top of that, we in this talk, we will demonstrate how to build some fundamental components and build some lower downstream application in spatial temporal modeling. Under this context, my recent research has focused on addressing some challenges in infrastructure research from the computer vision and machine learning perspective. And in this talk, I specifically narrowed down to the transportation related research problem. First, in addressing the lack of labeled data and suitable model, I will show how to efficiently and effectively generate and process sensory data with minimal human adaptation. And to address the limitation of AI algorithm to meet the real-world requirement, I first show how to bring active human AI collaboration to improve machines' flexibility and productivity. Also, I will show how to build a holistic simulation infrastructure to support design and development of machine learning algorithms. The talk contains a few set of my recent publication and ongoing research along three main directions. The first one is the spatial temporal visual and point cloud modeling. And the second one is the data-driven human AI collaboration. The last one is an ongoing project built on building a holistic traffic simulation infrastructure. Let's talk about the spatial temporal visual and point cloud modeling first. Why do we need to care about spatial temporal point cloud modeling? As I mentioned earlier, our world is a dynamic 3D world. We human beings continuously receive and interpret sensory data over time to understand the world. Let's first think about why AI works so well on images. First, it is ready to use. There are massive images that are available on the internet. For example, it is worth mentioning that pioneering ImageNet dataset has shaped today's thriving AI community by providing a massive open source data and labels. Besides, images are regular, order, dense, uniform, and arranged as image grids, which makes them simpler to analyze. However, all these do not hold for point cloud. Point cloud are not intuitive compared to images. Point cloud are irregular and not organized in a predefined manner, which requires suitable units to capture all the spatial neighborhood information. The point cloud processing problem become more complicated when we move from static point cloud to dynamic point cloud, which elevates the original 3D sparse processing to high dimensional 4D or even higher dimension sparse processing. When we initially investigated this problem back in 2019, most of the existing research focused on static point cloud processing and analyzing spatial temporal relationship from 4D point cloud sequences using AI operation was not well defined by them. For example, it was not clear before some of the early research attempts, such as the Minkowski engine framework for generalized sparse convolution on high-dimensional sparse point cloud. So under this context, my research have focused in advancing the understanding of motion and correspondence from dynamic point cloud sequences with minimal human adaptations. And before investigating motion and correspondence problem, I first explore the problem on how to achieve effective training and inference for large-scale point cloud in a purely distributed environment, such as a multi-load, multi-GPU HPC cluster. And I identify the main limitation of existing dense tensor-based frameworks, such as PyTorch and TensorFlow in processing sparse point cloud. I then developed the sparse pipe, an efficient and asynchronized pipeline parallelism framework that support distributed training for sparse point cloud. After making progress in the computational framework, I then moved to several fundamental problems of sample estimation, dynamic point cloud sequence modeling, and unsupervised shared correspondence. Let's talk about the sample estimation first. The definition of sample is very straightforward. We get two frames, we sample point cloud from the frames and compute or try to compute each point's movement. It is a low-level and fundamental understanding of motion in a dynamic scene and has many downstream applications, such as here, motion segmentation, human movement analysis, or motion prediction task. As a ground truth, point-wise adaptation are expensive and time-consuming to obtain. When we mention like the expensive, we basically means every single frame you are allocating like a millions scale points. So it's quite expensive and time-consuming to allocate. Therefore, the community actually prefers self-supervised learning to fully supervised learning. However, the problem lies on the fact that the existing self-supervised learning objectives are quite limited. To show that, I will provide an overview of the self-supervised learning for sample estimation. The idea is intuitive. Given a frame pair, let's denote source and target. Our goal is to move the source point cloud towards the target point cloud and try to keep them as close as possible, view matching to each point of the moved source to the target points and minimize their point difference. As a result, the movement obtained from the process can be considered as an estimation of the ground truth same flow. And in order to reach closer to the true motion, our job is to maximize the similarity or minimize the distance between the move source and target point cloud, such that we can actually using this estimated same flow as optimization for the true motion. And this framework then leads to the popular distance measure for point clouds. And currently, two popular measures called the chamfer distance and air mover distance have been widely adopted in the point cloud processing. They are used in self-supervised learning for sample estimation as well. However, the chamfer distance tend to suffer from the degenerate and many-to-one issues, while EMD is not a robust outlier and has a high computational cost. And in our research work, we argue that both CD and the EMD might not be the best choices. In fact, if you think about the point cloud, it's nothing but a basic sampling from the underlying data distribution. Given that, we therefore seek to represent the originally discrete point cloud as a continuous probability density functions and build two over-parameterized GMMs over the move source and target point clouds. By doing so, we can potentially capture the uncertainty in the point cloud generation process. For example, the jittering introduced in the LiDAR scanning process. Then our goal is to push the GMM of the move source to be similar to the GMM of the target point cloud for self-supervised learning. Then the core question is, how do we measure the similarity of two GMM? And inspired by the CS inequality, the Gaussian the inequality, and information theory, we noticed that the CS divergence has been proposed to measure the divergence between PDFs. In our research, we provide detailed derivation on how to plug GMMs into the CS divergence, and you will end up with a simple closed form expression. The key trick is to follow the Gaussian identity to obtain the product of two Gaussian PDFs. Here, I directly provide the resulting expression. More detail can be found in my paper's appendix. It's basically a three log sum exponential item. And if you take a closer look within each item, you have the exponential function inside each PDF. This is beneficial as the introduction of the exponential function can mitigate the oversensitivity to the outlier by suppressing large squared distance. And this is advantages compared to all the L2 distance approaches, including CD and EMD, where outlier can contribute large value to the loss and negatively impact the training. In the end, we are able to present a new framework for self-supervised sample estimation, where we predict the sample flow using a soft correspondence-based neural network, relying on optimal transport and one-step synchro iteration, which I skipped the detail here in today's talk. We then build the two GMMs over the move source and target point cloud. And minimization of the CS divergence between these two GMMs will lead to a end-to-end learning framework because the gradients can be backpropagated to the neural network for model learning. And we compare our CS objective against the popular CD and EMD to make a fair comparison. The only changing variable is the learning objective, and the model architecture remains the same. We can say that our CS objective significantly reduces prediction error and outlier and achieves a higher accuracy. To summarize, we have identified the main limitation of popular CD and EMD that are sensitive to outlier or computational intensive. We also introduce a lower framework that represent discrete point cloud as continuous PDFs and recovering same flow by aligning these GMMs, which is achieved by our CS learning objective. And we believe this could be very useful to the point cloud community. And then we'll move to the dynamic point cloud sequence modeling. As discussed, all the existing approaches either focus on a single or two-frame point cloud modeling, while the modeling of point cloud sequences is heavily underexplored due to a lack of suitable benchmark, problem definition, and suitable model architecture. To fill the gap, in this research, we introduced a new sequential sample estimation problem that estimates sample flow from point cloud sequences, while also investigating the sequential point cloud forecasting task. Our SSFE task is a novel extension of the existing sample estimation problem by moving from the processing of a point cloud pairs to a spatial temporal processing of 4D point cloud sequences. And to support the training and evaluation, we all need a new data set to help analyze the lower method. Therefore, we adopt two synthetic and yet challenging data set called Flying Sense 3D and Virtual KT. We basically reconstruct ground truth sequences and annotation based on the ground truth disparity map of disparity change, optical flow, and the long camera parameters, which are used in the fully supervised training and evaluation. For the self-supervised sequential point cloud forecasting task, we directly extract raw sequences from the real-world algorithms data set for training and evaluation. In the end, we are able to introduce three new data sets called the virtual KT sequence data set. I'm showing on the left. The middle one, the sequential Flying Sense 3D SFT 3D data set, and the sequential algorithms data set. This is the first benchmark for point cloud sequences containing diverse background and a multiple object motion in both synthetic and realistic environment. And to tackle the new problem, we introduce a novel recurrent cost volume that brings a classic cost volume in optical flow into the recurrent unit for point cloud sequences. We explore the nice property of spatial temporal point cloud processing. First, intra-frame order invariance. This basically means that for a given point cloud of m points, any permutation applied to that point cloud should not change the output of the model. This has been supported by many popular point cloud architectures, such as PointNet, PointNet++, and PointCount. Our model has it since our model built upon these architectures. Second, interframe location variance, which basically means that points at different timestamps may carry different spatial correlations. Such dynamic change of spatial correlation should be captured by a model. For example, changing the timestamp of a point, like shuffle it, should result in a different spatial vector. Our model can support it as our model is a recurrent model to maintain the location variance. Last, spatial temporal interaction between points. This basically means that points that are close spatially and temporally should be considered as labeling points, from where the local dependency should be modeled. This is also supported by our set-to-set cost matching cost design. Based on all this cost concept, we build our SPCM net as a strong baseline. And after establishing the new problems, benchmark, and baseline model, we then move to the evaluation. in these tables, all the baseline results are established and are reported by us. We're adapting some of the advanced model for point cloud processing. And it is clear that our proposed SPCM net has achieved better performance due to a lower spatial temporal processing unit for point cloud sequences. In the forecasting task, we also show that our SPCM net is better or competitive. Additionally, if we pre-train on sequential sample estimation and then fine-tuning on the forecasting task, it will further boost the forecasting performance. We realize the error in the flow estimation. Here, the red means more errors, and blue means less error. The visual results on the sequential sample estimation confirms that our model is better. We draw a similar conclusion in the evaluation of the sequential point cloud forecasting. To summarize, here we introduce a new problem for supporting the spatial temporal modeling of point cloud sequences and develop a lower recurrent set-to-set crossroom layers. And finally, we create a new benchmark to support training and evaluation. I'd like to share another research work done in the spatial temporal point cloud modeling, the unsupervised shape correspondence. Here, our main goal is to solving the shape correspondence by finding suitable feature representation between two shapes without accessing the ground truth correspondence for model training. The shape correspondence has many downstream applications in AR and VR. To list a few, we can map a tiger's texture to a human face, which we call the texture transfer. We can also transfer the pose of a horse to a camel for the mimicking task. And we can also stylize one object with respect to another object, or we can conduct the shape style interpolation between different animals. However, the current shape correspondence do have their limitations. Taking the classic functional map framework in shape correspondence as one example, it estimates the point-to-point correspondence by computing a linear transformation between two functional spaces built over two shapes. However, the typical optimization is always non-trivial and requires additional regularization or constraint, and it usually achieves a limited generalization performance. More importantly, most of them are required ground truth label on the correspondence. And in our research, we instead aim to design a new framework that can robustly identify some better feature representation for shape correspondence without accessing the ground truth correspondence, and end up with a self-supervised learning framework. And to address the limitation, here our high-level idea is to seek a mechanism that can enforce embedding of shapes in correspondence to lie in the same canonic or universal embedding space. To do so, we get inspiration from the classic local linear embedding algorithm. I'm sure some of you might get familiar with that by studying some machine learning, conventional machine learning algorithm. Basically, the classic LAE algorithm aims to preserve the local Euclidean geometry or manifold in both high and low dimensional space. Just give the audience a general concept of LAE. Its core idea is to assume that each sample can be locally locally linearly reconstruct by its labels in both high and low dimensional space. You can just simply think about like a small piece of paper, put a point on in the middle of the paper, and this point can be reconstructed by all the its label points lying on that plane. So locally, it's just a flattened space. That's what we call like preserving the local Euclidean geometry of manifolds. In our paper, we make a key innovation to generalize this classic local linear embedding concept to shape correspondence based on a novel cross reconstruction concept. More importantly, the whole training framework is again fully differentiable. More details could be found in our paper. The take-home message is that by doing so, we can inherit all the regularization effect from the classic LAE, therefore leading to a better feature representation. In addition, conceptually, our framework is also different from the classic deep functional map framework proposed by the Stanford researcher in terms of the linear transformation and the learning algorithm. The evaluation confirms that our model demonstrates better performance on the standard benchmark of human and animal shapes. Here's a visual result, again, confirms that our model is better with high correspondence accuracy under different error tolerance values. Here, the same color basically means they are in correspondence. Summarize, here we introduce a novel unsupervised shape correspondence framework, and by introduce a new LAE-inspired algorithm that represent map between shapes as a locally linear transformation, which leads to the learning of universal or canonic embedding of shapes in correspondence, and the model achieves a state-of-the-art performance on standard benchmark dataset. Now we'll move to the second session of data-driving human-AI collaboration. Here I will just showcase several research, past research I've done here. So at a high level, or in the data-driving human-AI collaboration, we try to integrate human intelligence into the data-driving human-AI collaboration, and it perfectly aligns with a larger initiative of human-centered AI. Along this direction, I developed the hybrid deep learning approaches for track and trainer classification. We observe that if you apply a pure deep learning classifier to a track and trainer classification, you will end up with a low accuracy because they fail to capture some fine-grained features from the track images. And to give you an intuition why it fails, when the federal government do the vehicle classification, they actually develop Federal Highway Administration standard in their traffic monitoring guide, which relies on some vehicle configuration, such as counting the number of wheels or tires, and counting how many trainer units you have for your track, and more specifically, whether you have a refrigerator unit. So that all these visual cues will help you distinguish different category of tracks. So I got inspiration by this classification schema and leverage both deep learning and conventional machine learning techniques to identify all these geometric and semantic feature. Like for example, here I will develop an object detector to detect wheels, and then counting the number of wheels, and also detect invent another refrigerator detector to detect whether the truck has any refrigerator, and so on and so forth. And we also calculate geometric information, like say the wide length ratio of the truck, because this will help distinguish some like big truck and large, huge truck. More importantly, once I got all the semantic and geometric feature, we are able to build a decision tree classifier on top of them, which is human understandable, enabling a successful collaboration with traffic engineering agencies. And here, this work shows how to integrate human intelligence for model prediction. In another work, I work on integrating human intelligence for data adaptation on Spatiotemporal. And we develop a human-in-the-loop perception pipeline of detecting and tracking, in which annotators recursively fix and refine adaptations imperfectly predicted by our tool, and incrementally add all this labeled data to the training data set, such as we can obtain a better single object tracking and multi-object tracking model. And by repeating the process, we significantly increase overall adaptation speed by 3 to 4 times and obtain better adaptations compared to existing adaptation tools. And also in the end, we are able to release a data set called Florida for pedestrian research. I'd like to transition to the last topic of building holistic traffic simulation infrastructure. So before diving into the detail, a story I want to share is that the big picture of intersection control in the past, today, and in the future. So it is interesting to know that the first traffic signal for controlling the road traffic with horse and pedestrian was installed in London back in 1868, operated by a gas light. And those first traffic signal controller were controlled manually. For example, or that is a police officer will give the right of way to a certain direction of traffic, and overseeing the approach to the intersection from a tower located close to the intersection. Today's traffic signal somewhat follow a universal color code, like red, green, yellow, and were widely implemented around the world. And many of them are fixed time the traffic signal with green phases duration usually depends on the traffic demand measured on an average day or estimate through model. And in the future, we can anticipate that all the vehicles are connected and automated. Therefore, the costly implementation of physical traffic signal controller might no longer be necessary or needed to coordinate the vehicle traffic. I basically say maybe in the future, we don't need a traffic signal anymore. Like every vehicle with the approach to the intersection, they will just talk to each other, like talk to the pedestrian, your phone, smartphone, so on and so forth. So you don't need the traffic signal controller at all. But you have to understand that this might not be ready for large-scale deployment in the near future. Like say, I'm talking about just next decades. And I also want to introduce some terminology on the traffic signal control. In a standard traffic intersection, you have the concept of approach, which refers to the road segment or lanes that directing your traffic into or out of intersection. And typically for each standard intersection, we will have 4 type of approaches, namely the north, south, west, and east approaches. And accordingly, based on whether you enter the intersection or you leave the intersection, you have the incoming approaches or outgoing approaches. And within each approach, you have the multiple lanes that serve as the basic unit of our approaches. Again, you based on the movements like enter or leaving the intersection, you have the incoming lane or outgoing lanes. Once you have that terminology, we move to the traffic movement. Here, it's basically describing a vehicle moving from an incoming approach to an outgoing approach. That basically say this is the incoming approach. You either go to this outgoing approach or this outgoing approach. So, or in a simple word, we just call it you make a left turn, go straight, or make a right turn. So that's the typical traffic movement. And for each traffic movement, we also attach it to a movement signal. Again, you see that like red, green, or yellow. So that's control the movement of the vehicle. And here, once you have all the move signal for each lane, the combination of all the movement signal will form up the phase. I like to show an example here. Like say this intersection, you have 12 for each approach, you have 3 lanes. So therefore, if you counting them clockwise, the first 3 lanes, you have the red light. So that's why you give a state as 3R here. Then you have another 3 red lights and another 3 for the south. And then you have the last 3 for the west, the incoming approach as green light. So those combination form as a phase. And for each phase, you also specify a duration. Basically means the states will remain static. Like say, they won't change like for here for like 31 seconds. And you can have multiple phase that like form up the sequence that will be executed sequentially. So that's basically the nowadays traffic signal control operation. And then after all the phase sequence and do some optimization, you form up a signal plan. Basically, like they set up all this initialization time, how do you coordinate the flow, and so on and so forth. When you have phase sequences, from phase 1 to phase 2, you need to make a transition, right? But you have to understand that in the traffic signal control, the transition of phase is not freely set. They have restriction. Like say you have to make sure those phase transition don't incur a conflicting movement. For the conflicting movement, I basically means you have 2 vehicle movement that might be potentially crashing or collision with each other. To give you an idea, say let's say here you have a vehicle stop here. You want to make a left turn to this outgoing lanes. So you make a left turn, and you also have a vehicle from the north that try to go to straight, right? So since if you have these 2 operations that happening in the same time, they might potentially hit in the middle of the intersection. So that's what we call a conflict. So if you check the conflict metric here, like they are not allowed. Left turn, go straight, they have a conflict, so you cannot do the translation for that combinations. But here I also demonstrate the popular translation like A, B, C, D, E, F, G, H that is used in the modern TSA control. And the diagonal elements is definitely non-conflicting because they are staying on the same limb and same direction. And once we introduce the basic terminology of TSA, I'd like to talk about some of our goal for TSA, which is also used in our paper. The first one is average travel time. We want to calculate the average duration spent by each vehicle traveling in the road network. This includes both the waiting time and the actual travel time. Definitely, like less travel time is better. The second one is the throughput. This basically calculates or counting the number of vehicles that have completely finished their trips. And definitely, if you have more hours, the throughput is larger. So we normalize it on an hourly basis. Third one, you have the queue length that basically counting the number of vehicle waiting on the lane. That is what you see when all the vehicles stop in front of the intersection and waiting for them to turn to the green light. And you also have the average delay. This one basically measure the difference between your mean vehicle speed on each lane and its maximal speed limit. So ideally, we wish all the vehicle can reach their maximal speed limits on our road. This is we always see that happening in the highway. Maybe everyone driving a car maybe more than 70 miles per hour, right? So average day, less delay is better. And we also have the accumulated waiting time that basically calculate the vehicle waiting time across lane over a specific time duration. And last, when we design the model, we also consider the environmental impact by calculating the total emitted carbon dioxide by vehicle. So that we can measure some potential impact to the environment. And for the traditional traffic signal control, we have roughly 3 main categories. The first one is a fixed time TSA. It's basically like switch a signal alternatively at a predetermined interval. And this is disadvantages when you have to respond to some dynamic change happening in the traffic scenario. And we also have the actuate TSA that captures some real-time traffic condition using some pressure plates or loop detector. But the downside for that method is you have some significant upfront and maintenance cost because you have to destroy the roads and bury some of the sensor. And you have the third category, the adaptive TSA, that is the modern TSA approaches. Where you leverage all the advanced sensor algorithm and just signal in real time. However, the main limitations are most of the control policy is heuristic or rule-based, and you have to carefully tuning all this hyperparameter requires a significant amount of domain knowledge. Here I want to show an example of a classic TSA method called a max pressures. The high-level idea is that for intersection, you counting all the vehicle from the green phase that entering the intersection. Like say here, you have 3 green lights. You're counting all the vehicle entering at this point. So that's the left items. You're also counting how many vehicles are leaving the intersection. So here you probably have four outgoing approaches, say here, and here, and here, and here. So they all leaving the intersection. So the pressure is basically measures the difference between the how many vehicle entering the intersection versus how many vehicle leaving the intersection. Imagine a case like you only entering all the vehicle entering the intersection and never leave the intersection. That basically means they will get stuck in the intersection zone, right? So that's when we have a high pressure for that plan. So for the max pressure algorithm, you basically say when you reach a minimal green time, you calculate the pressure for each candidate of green phases and only choose the phase that has the maximum pressure to transition to make a transition. And recently, we see the popularity of reinforced learning, and it has been explored to search all the optimal adaptive TSA policy for various intersection structure, mitigating the need for expertise to tune them one by one. This RL-based TSA method learn from scratch by interacting with the dynamic traffic environment and demonstrate some superior performance compared to conventional TSA approaches. Compared to the traditional TSA that aim to minimize traffic objective subject to a specific traffic model, the control policy from the RL is adaptive that can be adjust on the fly through learning from the data itself, while the traditional TSA has to design a static function or a predefined rule for controlling the signal. So here, at least we demonstrate it's somewhat promising to pursue some RL-based TSA in the near future. And I'd like to share a typical reinforced learning-based TSA pipeline. So typically, when traffic engineering working on this problem, you first identify your area of interest from some OpenStreetMap website. Basically dump a Google Map like data from the internet. And you also have a mechanism to collect some traffic data customized to that region. So the traffic data, so you combine both the road geometry and the traffic data to create your scenario description. And once you define that scenario description for both static and dynamic object, you are able to create a simulator on top of that. And then in the simulator, you can interact with reinforced learning framework and do the single control policy optimization. After you finish all this training loop, we can also design some monitoring mechanism to evaluate the performance, which is what we mentioned before, the objective of TSA. And do we miss something? Yes. The current study of RL method, which I call feature-based RL TSA, are still significantly insufficient as they are operate and verify under a strong consumption. Here, the strong consumption means that when they collect all the observation, they assume an ideal perception algorithm. Say you already know the precise number of queue lengths of each lane or waiting time of each lane. This is unrealistic in reality because if you're working on a real world intersection, most of the time you only have camera data. You only have a camera and video, and you have to do some video processing to obtain all this equivalence waiting time measure. Given that, so it's fair for us to say that in real world setting, this high level statistics are difficult to obtain because you never have an ideal perception algorithm. And we also have another critical issue because all the features from the existing RL-based approaches are leveraging some manually engineering feature that cannot comprehensively represent might not capture the intricate traffic scenario. For example, if you are interested in understanding the interaction between pedestrian and vehicle, and your design feature only calculating the equivalence of vehicle, then you actually miss this important information of pedestrian location and intent. So given that, it's fair for us to say that all the manually designed high-level feature might not sufficient to support some downstream application in TSA, especially when you want to pay attention to security, safety of the pedestrian. And given that, I'm currently seeking a promising direction, which is basically have three key components. The first one is we want to do some invent some end-to-end policy that is digest the data like from the camera LiDAR and then predict the policy in an end-to-end framework. And to support that, we also need to have a visual data that enable your model to see the world. And we also need advanced simulation. Here, the basic means that for some scenario, TSA, like if you're talking about understand the safety of pedestrian, in the reality, it's difficult for us to collect sufficient number of scenario that is intentionally a traffic accident, while it's easier to do that in a simulator. Given all these three key components, this leads to a holistic framework towards a vision-based traffic signal control. We do have some challenges there. The first challenge is there are much less work exploring vision-based TSA. And most of the TSA policy are limited to some oversimplified or top-down cartoon-like snapshot, which has a huge synthetic to real gap from the real world. And most of the simulation are 2D simulator, and they cannot leverage or study the multi-view camera setting in a 3D world. Given that, it's fair for us to say the current literature cannot tackle vision-based TSA using the existing research infra or traffic simulators. Again, that leads to our traffic dojo framework. So framework of our traffic dojo is demonstrated here. We basically introduce a traffic dojo that is a traffic signal simulation framework that bridges MetaDrive with microscopic simulation and facilitating the research of vision-based TSA policy. And to facilitate the standard reinforced learning library, we also follow the standard open AI GYM interface and provide a TSA environment that enables capturing visual data from the multi-modal sensor, including RGB cameras, depth camera, semantic cameras, LiDAR that could be positioned anywhere in the 3D environment. And the system is programming in Python and will be open source shortly, and making it accessible for the both the computer vision and transportation community to contribute. And there are some key features of Traffic Dojo. The first one is a map manager, which basically trying to conduct seamless transformation of a road network between different simulators. For example, here the Sumo and MetaDrive. And it also supports the importing map and editing map. You leverage some tools such as Sumo GUI. And we have the synchronization manager that is directing the synchronization of creation, updating, removal of vehicle and pedestrian into simulators. And we also develop a traffic signal agent manager that take charge of the traffic signal control at intersection, responsible for receiving critical information and making transition between different traffic phases. And we have the observer function that allows you to place the different sensors such as LiDAR, camera, depth sensor into your 3D environments so that you can see a traffic scenario from any modality and any viewpoints. And we leverage the MetaDrive. The high-level working mechanism of MetaDrive is make a transition between states. The standard definition of a simulation. And in our framework, we consider both Sumo and MetaDrive, and we choose them as a key simulation tool within our framework. And MetaDrive specifically stand out as a lightweight and flexible framework built upon the HANA 3D. It offers some precise physics simulation and supports a range of sensor input, including RGB, LiDAR, semantic, and depth map. Noteworthy is MetaDrive's remarkable balance between visual rendering and physics simulation, achieving up to 300 FPS on a standard PC with just a single instance of 100 MB in size. And our Traffic Dojo integrates MetaDrive, thereby inheriting and embracing all the distinctive features within it. However, the MetaDrive do have their limitation in its ability to comprehensively analyze some diverse traffic flow condition, primarily due to its original design focused on short-term self-driving scenario from the ego vehicle perspective. Hence, here we have some seamless integrate Sumo, an open source framework that supporting microscopic traffic simulation into our Traffic Dojo. And the choice is attributed to the Sumo's exceptional capability in efficiently managing large-scale network and accurately simulates a realistic traffic flow. And we make efforts to bridge in both MetaDrive and Sumo for large-scale traffic simulation. And while you might hear about the Scala that also offering a co-simulation with Sumo, but it seems to be limited in this scenario because they are quite heavy and running slowly, very slowly. So given that our main goal is like in a Traffic Dojo, we want to offer a more practical choices for research to train and test their algorithm and protocol, focus on specifically on the downstream TSC application. Here are some examples from the Sumo simulation on a 2x4 grid of intersection, which is very fast to run. And this is a demo for our Traffic Dojo. We are able to connect the Sumo and MetaDrive and display them simultaneously. And we also provide the bird view BUA map for describing the scenario. And we can also place multiple camera in the same so that you can potentially contribute to the multi-view computer vision task. And in the traffic dojo, we also implement traffic signal controller, which is demonstrated here, that coordinates the traffic at a single intersection. And in the traffic dojo, we also establish some benchmark and baseline. For now, we only consider some baseline controller, considering the popular fixed time, self-organized traffic lights, or max pressure. We also consider some RL controllers for establishing the baseline. And from the experiment result, we have several key findings. It turns out that even we talk about the promising of RL, TSA, but the benchmark tells us the traditional max pressure still perform very competitively compared to all the RL approaches. That means there's still some performance gap between the RL and some of the advanced conventional TSA. The second finding is that if we move from the facial-based TSA to vision-based TSA, that basically means you using the Q lens, replace the Q lens with camera data, you still see some performance gaps there. The third observation is that when we explore the vision-based RL with a bird view, it seems to be perform better compared to multi-view. So I guess there's still some research gap to identify how to successfully fuse camera information from multiple angles. And we also justify that if you add some noisy to some feature-based approaches, you do see some performance drop. And this is just a showcase for our current traffic dojo, we only focus on the vehicle movement, but we actually still have some ongoing project to incorporate pedestrian. I'm not sure whether you can see it. So in the future, we want to incorporate the pedestrian into the traffic signal control, so that you might incorporate the interaction of pedestrian and vehicle into your TSC optimization. So for the traffic dojo, we present a holistic traffic simulation framework towards a vision-based TSC, and we released a benchmark for training and testing TSC, and the experimental result highlights the promising potential of the end-to-end learning, and it opens new research opportunity to both reinforced learning and transportation community.